Learning outcomes. Upon completion of this lesson, students should be able to define a SCADA system, describe the differences between SCADA and DCS, describe the differences between an HMI and a historian, define an MTU, RTU, PLC, PAC, and an IED. Describe a safety system. Describe basic safety system functions. And differentiate safety from security. First, let's look at the Supervisory Control and Data Acquisition, or SCADA system. SCADA systems are made up of instruments, computers, and applications that provide controls and data acquisitions for essential commodities and services for our daily sustenance and activities. SCADA systems play a major role in our critical infrastructure and require a high level of protection from threats propagated through physical or electronic media. The interdependence of critical infrastructures has been investigated intensely and identified SCADA communications as a common link between these systems. SCADA systems collect data and perform centralized monitoring and control. An HMI is the interface between the operator and the SCADA system. It provides graphical and textual displays that facilitate the control and the operation of the system. Further, the HMI provides the operator critical alerts and insights depicting the status of the system. A data historian is simply a database of events and information on devices and processes in the SCADA system. It may either be an in-house designed and implemented database system, or a more robust commercial-grade database system, such as Microsoft SQL Server or Oracle Database System. A PLC is a self-contained computing device that is geared mostly for industrial control. It is programmed to realize the various functions required by industrial processes, such as robot controls, equipment operations, and status diagnostics. The PLC instruction set may include logic, timing, counting, communication, math, and input-output I/O control. An Ethernet-enabled PLC is shown in the diagram below. A PAC is very similar to the PLC, but contains more elaborate functionalities, such as faster processors, advanced communication capability, database integration, and advanced adaptability. An IED facilitates the communication between the MTU or RTU with polling field devices such as actuators and sensors. In some instances, an IED may have analog input sensors, analog output, communication systems, and program storage. An example IED that collects data from multiple sensors is shown in the diagram below. An example SCADA system layout depicted in the figure below shows the components and general configuration of a SCADA system. The control center, which collects and manages field data, includes the network routers, the HMI, engineering workstations, and the data historian. The field sites may include the PLCs, the IEDs, the actuators, and the data gathering sensors. The communication between the field devices and the control center is facilitated by a wide area network, WAN, comprised of devices operating on various communication channels such as radio, satellite, broadband, Wi-Fi, optical fiber, cable, or telephone lines. In contrast to the previous SCADA layout, the International Society of Automation's ISA 95 standard delineates the SCADA architecture into 4 levels: production and control process, supervision and monitoring, operation management, and business operation management. The 4 operating levels of a SCADA system are detailed in the following: production and control processes. This level includes the control and manipulation of physical processes and consists mostly of PLCs or RTUs. Although the activities within this level do not directly interact with production processes, they can have a direct impact on processes. For example, the measured value by a sensor may not directly feed into the production process, but may have a major effect on controlling the efficiency of the process. Supervision and monitoring. This level includes the supervision and monitoring activities of control and production processes. At this level, software and hardware systems such as HMI and switches and gateways are provided to enable monitoring, control, and supervision capabilities. Operation management. This level includes the systems that are tasked to carry out the manufacturing processes and operations management. At this level, the data historian and the security applications such as firewalls and intrusion detection systems, IDS, intrusion prevention systems, IPS, are located. Operation business management. All business-related activities and solutions such as enterprise resource planning, ERP systems, and business intelligence, BI systems, are found at this level. Primarily, the software and hardware systems at this level are installed to provide support for the overall management of business activities. Next, we will look at the details of distributed control systems, or DCS. Here are some definitions of DCS. The Automation Systems and Instrumentation Dictionary defines DCS as the control achieved by intelligence that is distributed about the process to be controlled, rather than by a centrally located single unit. NIST SP 800-82R2 states that DCS are integrated as a control architecture containing a supervisory level of control overseeing multiple integrated subsystems that are responsible for controlling the details of a localized process. An example DCS implementation is depicted below. The multi-level DCS includes components from the field level all the way up to the enterprise level. Similar to the SCADA system, a major subsystem at the supervisory level includes, among other things, the control server, the HMI, and historian that facilitates management, monitoring, data gathering, and control capability for the system. The control server communicates data set points to and from the distributed field controllers, which control their process actuators based on control server commands and sensor feedback from process sensors. SCADA systems and DCS, at first glance, appear to be very similar. Although there are very striking similarities between the two systems, there are also prominent features that distinguish one from the other. The similarities between a SCADA system and a DCS are most likely found in the components that they employ and the functionality of each of these devices. The components include, among other things, the HMI, the historian, the PLCs, and the control server. The main differences between a SCADA system and a DCS are in their respective operational focus and scope. On operational thrust, a SCADA system is event and data driven. DCS is process driven. On operational scope, a DCS system is more dispersed, spanning multiple geographical locations. DCS is mostly limited to a local environment, such as a factory or manufacturing floor. On operational control, a SCADA system, which is designed primarily for system monitoring and data collection, has limited process control capability. DCS, with its multiple controllers, has the capability to implement advanced process control techniques. In some implementations, such as those in the electric power generation facilities, the DCS works in conjunction with SCADA systems. The DCS controls the operation while sending information to the SCADA system to control production output based on transmission and distribution demands. Thus, one can perceive DCS as an integrated control system that manages multiple control subsystems that are responsible for the operation of local processes. The control is usually achieved by deploying feedback or feed-forward control loops to automatically maintain desired set points. We will closely look at this in subsequent slides. With an ever-increasing demand on immediate access to operational information for just-in-time decision-making, DCS as well as SCADA systems are becoming more integrated into the corporate network. Thus, the complexity of integrating information technology, IT, with operational technology, OT, becomes an additional issue to the information security landscape. We will now focus our study on safety systems. The American Society of Safety Engineers defines safety as the state of being relatively free from harm, danger, injury, or damage. A compliance-dependent approach to safety, relying on codes, standards, regulations, and one or two engineers, is not an optimum methodology. As pointed out by Stevenson, standards and regulations tend to lag behind rapidly changing technology, which could possibly prevent the achievement of optimum safety. By adopting the proactive system safety approach, risks and hazards can be identified early and control mechanisms can be put in place to mitigate or prevent those from happening. The difference between safety and security is not well defined. At times, the two terms are used interchangeably. One way to look at this is to think of safety, as defined above, as being the state of being relatively free from harm, and security as the assurance that safety remains constant. At the very least, people working in an industrial setting should recognize safety and security are complementary and should be treated as such. The purpose of the System Safety Program Plan is to identify the specific system safety requirements for the entity, product, or environment that is of interest. The preliminary hazard list document enables the initial assessment of hazards identified early in the life cycle of the entity, product, or environment that is of interest. The preliminary hazard analysis document is an extension of the preliminary hazard list. It contains additional hazards, the hazard analysis, recommended controls, and the level residual risk after the controls have been applied. The hazard tracker is a living document. In a way, it keeps a historical record of all hazards encountered, the corrective actions, and the controls that are in place to mitigate or prevent those hazards from becoming realizations. The Subsystem Hazard Analysis document provides a detailed analysis of each hazard associated with a specific subsystem. The Operating Hazard Analysis provides a detailed analysis of hazards that pertain to the operations and maintenance of the system. This includes human factors such as procedures, training, and machine interfaces. The Change Analysis Report contains the safety analysis associated with system changes or patches. The Accident Analysis Report documents an analysis of each accident, the cause including associated hazards, the controls in place, and the mitigating or preventative actions taken. With the advancements of automation, safety systems are designed to be heavily instrumented and interconnected. Thus, the advent of Safety Instrumented Systems, SIS. SIS are installed to protect humans, physical assets, and the manufacturing environment from hazardous conditions. More specifically, SIS are instrumented systems used to implement one or more safety instrumented functions. As described in IEC 61511-1 mod, there are two basic safety instrumented functions: continuous or on demand. The continuous functions are referred to as safety instrumented control functions, while the on-demand functions are the safety instrumented protection functions. Automated processes are needed to efficiently implement these safety instrumented functions. To accomplish that goal, application software needs to be designed and developed. The application software safety requirements should include the following functions: a function that enables the process to remain in a safe state, a function that will monitor and manage system faults, a function that will provide an online testing of safety instrumented functions, a function that can provide an offline testing of safety instrumented functions, a function that will facilitate the safe modification of the SIS, and a function that interfaces with other non-safety related functions. At the very least, people working in an industrial setting should recognize safety and security are complementary and should be treated as such.